So this is the extension of the problem that we did last time. What we did, we found the effect size, we found the standardized effect size. What is the difference between the two? The effect size is simply, you can tell me, 1, so the predicted value, we'll call it mu1. What did I use last time?
mu1.
Mu1 and mu0?
Minus just mu, I think.
Mu, okay. And it really doesn't matter. If I have to write this, I will write this as x bar because it is coming from a sample. Your book isn't making that distinction, and I don't want to confuse you when you do that. At least they're not making that distinction in this chapter. But proper notation here would be x1 bar or x bar. So they use the sample of size 100. We have an effect size of 1. We have alpha of 0.25. Standardized effect size is simply mu1 minus mu divided by sigma. And last time I mentioned that one would prefer a standardized effect size under certain conditions. What is that condition? So if I have two populations, it is better to standardize because one might have too much variation compared to the other. But either measure will work. And this is where we stopped. Yes? Last time. Great. The problem had a couple of other parts. They wanted to sketch type 1 error or alpha. Type 2 error and the power. I mentioned that we're not going, or I'm not going to ask you to sketch stuff on an example, but given a picture, you should be able to interpret that picture. If you encounter a problem on my lab that says, oh, sketch using this graph, and you have to drag your mouse to sketch a graph, that means not needed. Interpreting a graph, different story. They are giving you the picture, you just have to interpret it. You have to let me know. I know that there aren't any problems where you have to sketch, but if you run into one, let me know. That's it. I will sketch so that you get an idea on how to compute power and type 1 error, type 2 error, etc. Before I left my office, I wrote an R program over the weekend. I copied it to my USB drive, and I left it. I'll show it to you next time. That is, if I remember to bring it. It's not needed for this class anyways, I just wanted to do something extra. I'll draw that real line here, leave it as is for now. So the top distribution is the null distribution. Null distribution is also known as comparison, reference, very good. And I got the EM part. My brain was going back. Comparison, reference, etc. So in this case, our reference distribution is centered at what value? There are a whole bunch here. Let's know which one are we picking? 90, very good. So the reference distribution is 90. Last time I said you don't have to sit around plug it in the formula x bar minus mu divided by sigma to find different points here. How did we come up with, a few points in the middle of the line? What did we do last time?
Use the standard deviation.
And then what?
Added it to
Okay,
90.
to 90. So, Sarah, did you have something? Same thing. I can see the look. 90, 94, you add 4 again, 98, 4 again, 102, subtract. 86, 82, 78. Good. No distribution. We will get to this in a second. Now, we want to know where a type of error needs to be specified. The problem gave us that it is a one-sided test. Agreed? So we are testing to see an effect either on the right or the left. Your book refers it to as high, low. Looking at the predicted mean, you are testing for the predicted mean. What test should we choose? Right, left, 210. Right, very good, because I have 91 higher than a reference value of 90. Since I'm picking a right tail test, one-sided, the area that I'm going to shape will correspond to the type of error, and that has to be on the right side. Going back a few classes, if we have to come to a conclusion for a test, we need a cutoff score. Yes. I wrote a bunch of cutoff scores last time, or a while ago, for a given value of alpha. If you have a standard normal, mean 0, standard deviation 1, we wrote a tiny little table, we had a bunch of values. Yes, we also did problems using that. You don't have to memorize this, you get to have a cheat sheet in this class. Definitely in there. I know from experience that for a value of alpha, right here, the cutoff score on the right hand side is 1.645. Yes. If you look at the graph, it doesn't make any sense. Right? This is 1.645. It's like 90 something. How am I going to draw that area? Right.
Is that like a little over 1.5 standard deviation?
1.5 standard deviation, okay. Any other answers? I'll give you a hint. We all agree that that is a normal distribution, yes? Standard is the key word. What is the difference between just any normal distribution and a standard normal distribution?
The 90 would be 0.
Very good. The 90 would be 0. A standard normal distribution has a mean of standard deviation of 1. The reason why I'm doing it this way here is to show you the relationship between alpha, beta, power. For the sake of this problem, I wrote it this way. If you look at the work that we did last time, I wrote 0 below that 91, 94, 2, 98, so forth. By all means, null distribution cannot have a mean specified, mean such as 90. So the null distribution is standard normal, mean 0, standard deviation 1. The only reason why I'm doing it this way is to show you alpha, beta, and power. Good. Keep that in mind. The cutoff for a standard normal is 1.645 if alpha is 0.25. Even though I've moved the normal, I can use the formula of the z-score to find the cutoff when the mean is not 0. Good. How do we do that? That is the formula for z-score. Sum observation minus the mean divided by the standard deviation. If I rewrote it, algebra, multiply both sides by sigma, move the mu to the other side. That's what you do. I simply did basic algebra. Now I know what the cutoff score is. Yes, 1.625. I know the standard deviation. It is given in the problem for mean 90. Don't use your calculator yet, and don't cheat. You have to tell me as to whether whatever number that we will compute, will it lie between 90 and 94, 94 and 98, 98 and 102. Where would this number fall? Clearly, it has to be on the right hand side. Yes, because I'm adding the name.
Between 94 and 98.
Why?
Because a z-score shows, a z-score means over one standard deviation one. So over one means it's between 1 and 2 standard deviation.
Very good. So if you go back to the last class, I simply said each of these points, when you convert it to a z-score, will be 0, 1, 2, 3. What does the z-score measure? It measures the number of standard deviations you take from the mean on either side. Yes. 1 standard deviation, 2 standard deviations. So what I have there is 1.645. So it has to be between those two values. Good. Now you can use your calculator and tell me what you get. 96.3. Over that, 96.6. 96.58. I got the 6. So we'll keep it as 96. Perhaps it is somewhere here. Good. Good. So we have the null distribution expressed in terms of the mean. When we do an actual test, it's sort of just a reverse process. You take this, convert it to the null distribution. We'll get to that later. Now we want to sketch the predicted distribution. At the end of class last time, we did sketch it. Yes. Now, what did it look like? Did it have an overlap? Did it not have an overlap? It had an overlap, but not a lot. So we are going to start at 91. 90 is there, 94, 23. 91. Good. What was the standard deviation? We used the exact same standard deviation as sigma equals 4. So 91 plus 4 here, 95, 95 plus 4, 99, 103, this side, 87, 83, 79, 74. Good. And you may ask, well, why is it drawing it separately this time? Well, I want to show what beta and power are. That's why. Good. Just assume that it is a similar bell curve because I'm not perfect. Oh, not bad. But the curve doesn't look like a bell curve, right? I'll give it a try one more time. It's bothering me. Not that great. With me? Now, this distribution is the alternative distribution. Because you are looking at a mean that is greater than 90. So you're asking yourself, well, if we go with the sample, what would the distribution look like? This is what it's going to look like. Last time I simply drew this on top of that. We saw that tiny little shift. Same thing, that little shift is observed here as well. How do we compute the power? I sketched alpha. If you find the power, you can easily find beta, because beta, the type 2 error, is related to power. Do we remember how? How is type 2 error related to power? I'll give you a hint, there's a minus. Not that great. Literally.
Oh, I was gonna say, is power like a type of how the thing gets into your?
No, beta is the progressive type 2 error. Beta. It's 1 minus beta. So power is simply the complement of beta. So if you know the power, you can find beta. So how do we find power? So probability of rejecting the null when the null is false. Well, if I'm not looking at the top curve, I'm looking at the bottom curve, the null is false. Do you agree? Because I've moved away from the null distribution. I'm talking about the alternative distribution, which simply means that the null is false. I want to find the probability of rejecting the null. How did I reject the null? Above, I found a cutoff there. Using that cutoff, I found the cutoff for a mean of 90. And I said, well, if it fell about that, I will reject. Agreed. Repeat the same process with the alternative. Alpha, probability of rejecting the null when null is true. Power, probability of rejecting the null when null is false. Good. We are finding power because once we have power, we can easily find probability of time to go. That makes sense, right? Okay. So that would simply mean I need to find the number that corresponds to that line, cutoff of 1.645. I can use the same process. What will change? 1.645 is the cutoff with the standard normal. I'm moving away from the null to the alternative, and I would like to know if I can draw a straight line, what that point is. How will we find it? I'll give you a hint, you've got to use that formula. What will change in that formula? Riley? Yeah. Mu. Mu is going to change. If signal were to be different, signal would change. Agreed? So mu in this case will be 91. And this part doesn't change. By all means, you shifted the curve by 1. So this number is simply, yes, 97.58. Good. Let's shade this. That area is power. Power is probability. We need the calculator to find power. This probability is just alpha 0.05. I want to know what that probability is. Do we remember from 2023? So we already know the probability above 96.58 is 0.85. We started with alpha, we found that number. I don't know what power is. I'm going to find it. Your book might suggest use the table. Don't. Just use the calculator. We have the technology, so let's put it to good use. So press second, the Mars button right next to clear, and you should see Obsidian. If you have the newer version of the calculator, your screen will look different than mine. What is your screen? Lower, upper, new, is it signal? Signal. It simply tells you what the lower end point should be, upper end point should be, and the mean and the standard deviation. Let's look at the top curve that we were talking about, the null distribution. I shaded an area. Yes. Well, where did the area start? At what point did the area start? Riley,
So 96.7.
96.5. Do we agree? Yes? Okay. Now, it ended, or supposed to end somewhere down the line, on the rear of the line. Some professors might say, we'll pick a large number. I say, why don't you simply pick infinity, right? The calculator has bounds, so in the calculator, infinity corresponds to E99. So press the second button, the blue button, comma, you get E, simply put 99. That would mean positive infinity. Next, you want to specify the mean and the standard deviation. Once we enter this, don't type enter and get the value, just wait. What was our mean? 90. Standard deviation? 4. Okay, don't hit enter. Even before we start, I'm going to ask you, what should the answer be? The answer corresponds to the shaded area under the curve, which is simply the probability of type of error.
This is the 0.05.
It has to be 0.25, that's what Riley says. Do we agree with that? Yes. I do too. 0.04998. Isn't that 0.25 approximately? Okay. Now, if that is the case, I can repeat the process with the alternative and get the power. Correct? Okay. Repeat the process and tell me what the power is. So 97.58 seconds, comma, E 99. 91, comma, 4. And you do all that, you still end up getting 0.04998. Well, that sort of tells us no matter what mean you have, whether it's 90, whether it's 91, doesn't matter. Your power will always be equal to alpha. Do we agree with that? Would the power of power is the ability to the probability of a true positive. So no matter what you do, no matter what the mean is, alpha would equal to power. Does that make sense? In other words, probability of false positive would equal to the probability of true positive. Is that what we want? Or do we want the probability of true positive to be higher? I guess Riley?
Yeah, you want true positive to be higher.
Right? I want the chances of the true positive to be higher. So alpha is the probability of a false positive. Beta, oops, we'll do power. Power is the probability of a true positive. In other words, if there is a difference, you have to pick up that difference, or else the test is useless. Do you agree? Based on what we did, no matter what mean I have, maybe 90, maybe 91, I always end up getting I will always be getting alpha equal to the power. That can't be right, yes? So, let me recalculate. So something is off. What is so good? So this cutoff oftentimes people will shift and pick the cutoff from there to there. That's exactly what we did. Shifted by 1. We got it as 97.58. Keep in mind, since that is fixed, if you shift that curve, you will get the exact area. Agree? If you simply move that picture by 1, the entire picture, you are going to get the exact shaded area. With me? Very logical. So, the true cutoff in computing the power, see, does correspond to that number, but if it corresponds to that number and you drop it down here, where will it fall? Will it fall at 97.58 or will it fall at 96.58? That number is 96.58. Do we agree? I'm going to drop it directly down to this scale. Is it going to land on 96.58 or 97.58? Let's say it matched perfectly the 2 lines. Real number line 2 is right here. You drop it down. Where will it be? At 2. So I want you to fix the real number line and then the curve shifted. The curve is the one that shifted. Yes, the real number line didn't shift. Do you agree? The curve moved its position by a tiny bit, moved to the right. The real number line didn't change. So when we drop this down here, will it fall at 97.58 or 96.58? 96.58. The reason why I did it this way is because oftentimes people would overlook this part that the real number line stays fixed, and what changes is simply the curve. The curve shifts, in other words, the area is the one that's going to change. If you shifted the real number line with the change in mean, you will end up getting the exact same error. That's what I illustrated. If you started with the first mean, look at the very first probability we computed, 96.58 and above, gave you 0.05. Shifted the real number line, 97.58 and above, gave you 0.05. Not right, correct?
So you'll always just be the first z-score.
But with the second distribution. Exactly where I was going. So don't make this mistake. It's a very subtle mistake. I wanted to demonstrate that, which we did with the calculator. We're not shifting the real number line, we are shifting the curve. If the curve moves, the area is going to increase. Pick up your calculator, find the area above 96.58, same z-score cutoff, but with the alternative distribution. So the power happens to be 0.08157.
0.8507.
Okay. That's good enough because going to represent it as a percent, we'll have 8.15%. Good. Okay. The power, the probability of a true positive is only about 8.15%. Good. True positive would mean I reject a no when you're supposed to. Positive means reject no. Negative means do not reject no. In our case, if I asked you, should you reject the no, given the fact that the true mean or the population mean is 90, standard deviation is 4, you are the researcher, you predict it is higher than 90, so you claim that it is 91, and you're going to have the same standard deviation. So we moved away from 90 to the right. At the end of class last time, we actually knew the conclusion. I asked you, well, do you think that we can reject a no in this case? What did you guys tell me? The very first case, Father.
There's a, I mean, 8.15% for getting a true positive, that's not very good.
We will get to that in a second. So last time we actually ended with the conclusion. I asked you, well, if the no is mu less than or equal to 90, and the predicted value is high, which is why we did a right tail test. Yes, we did a right tail test because the predicted value or the researcher says, no, it is not 90, it's bigger than 90. Hey, I found it to be 91. Okay, you are making a statement. I want to know if that 91 is significant or not. Is it different from that 90, given the fact that the standard deviation is still 4? I asked you last time, should we reject the no? And a good amount of people here said we should not reject the no last time. Why did you say so? There was a word, we can play the word game, but how to? Seven-letter word, starts with the letter O, ends with the letter P. Very good. Overlap. Last time we said, well, we should not be rejecting the no because the alternative distribution that we drew overlapped to a great amount with the no. Yes. So it is no different from the no. That was our conclusion. Yes. This time, we're simply putting what we saw visually in terms of numbers. What is power? Power is simply rejecting the no when no is false, the probability of it. In simple terms, it is a probability of rejecting the null when you're supposed to reject the null. That's all this means. Null is false would mean you're finding evidence to the alternative. If someone asks you, well, what are the chances that whatever conclusion that you have is a true positive? In other words, 91 is in fact statistically different from 90, greater than 90. What are the chances that that statement could be true? 8.15%. Do you agree? Is that a good probability? I'm going to write that in words. Can I erase this part right here? I don't want to erase this. So you look at the value of power. This is a simple interpretation. Rejecting the null what I wrote here is probability of a correct decision in rejecting the null, that is mu greater than 91. Sorry, mu greater than 90, based on the predicted mean of 91 and sigma equals 4. The sample size is given in the problem as 100. Read the statement. It is the probability of making a correct decision in rejecting the null. That is, you are going to not say average is less than 90. You are the researcher. Hypothetically, you say that mean is bigger than 90 because my study gave me 91 as the average. Standard deviation prevents to be 4. So based on this value, you make a statement that I'm going to reject the null and conclude that I've found an effect. Yes, effect going back to several classes ago, effect positive, one and the same. So probability of the correct decision in rejecting the null, that is, you're saying that there is an effect. You found positive, you found a true positive based on the predicted mean of 91, sigma to be 4, sample size to be 100, and the chances of that correct decision is 8.15%. Good. Now I ask you, did you make the correct decision?
Yeah,
Why?
because that's a really low percent chance. If you do reject a null, that's gonna be correct. And we
Go on, keep going.
did not reject the null.
I don't want you to look at anything else. Just read the statement and tell me that if you rejected the null, are you making a correct decision?
It's a low probability.
Very good. So you can't go back and forth between null and reject. Got to look at the interpretation. What does it say? You're rejecting the null, and what does power mean? Rejecting the null when the alternative is likely or the null is false. So the statement here is the probability of making a correct decision in rejecting the null, which would simply mean a true positive. Probability of concluding that you have a true positive based on the evidence that you have is 8.15%. Keywords here, correct decision in rejecting the null. What are the chances that you made a correct decision in rejecting the null? If that percent is small, if it is only 8.15%, if someone says, oh, there is only an 8.15% chance that you could be right or that you are right, then is that person right? No, that's exactly what I'm saying. The probability of a correct decision in rejecting the null is only 8.15% based on the data. So did I make a correct, or will I be making a correct decision if I rejected the null? No, I'll be making a wrong decision. Yes? So in this case, we should not be rejecting the null. Good. What is a case when you should, or you will be having a good amount of power? Here is a case that I'm going to draw. On the same real number line, now that I've explained this. 90, yes. We got 96.58. Good. I'm going to shift the entire thing and draw it in blue. I'll call that 105. Good. Same Z-score, yes. With the purple curve is the null distribution. Yes, the one on top. The blue one is the alternative. I'm not a great artist. Technically, they should look the same, but oh well. I know what the area above 96.58 is. One up there, 0.5. Agreed. So I'll draw that in purple. So the area in purple is 0.05. The bottom curve, I made it very clear that the real number remains the same. What gets shifted is the curve. That's what I think. Good. I didn't want to start with this because you will have difficulties understanding how. Now that I've done it separately, you can visualize it together. Same cutoff. If you found the area above it with the null distribution, you get answer. Yes. Same cutoff, but if I use the alternative distribution, what will I get? What has a name? Using the same cutoff of 96.58, you find the probability about the area about, I gave it a name, the answer is right there. Louder, listen.
The power.
The power, same cutoff, 96.58, area above. What I computed was the power. Good. Power is the probability of a true positive, 8.15%. Look at this picture. Let us not compute power yet, but I'll simply ask the question. Do you think that we have a true positive here? In other words, that we can conclude that the average is bigger than 90. Sarah? Why?
It's not a whole lot of overlap.
There is not a whole lot of overlap. Yes? Not only that, the difference between those two is the effect size. Do I have a large effect? It's a huge effect. That's it. Pick up your calculator. Same cutoff, but you're going to find the area using the blue curve. So area under the blue curve using the same cutoff of 96.5 would mean the value of the mean that you use in normal CDF has to be listen.
Is it 105?
Is it? It is 105 because I'm looking at the alternative. Mean is 105. I'm not changing the standard deviation, just like that, the previous case. Few of you already suggested that, oh, we should probably reject the null because the effect size is large, there's not a lot of overlap. So are we making a true, if we made a true positive, what are the chances that we are making incorrect decision? That's what you're computing. What did we get?
0.9823.
So here, power is the probability of rejecting the null when null is false. In other words, we're looking at the alternative. In simple terms, probability of a true positive. Correct decision, probability of a correct decision. Beginning of chapter 6.1, they started by saying decision errors. This is what we mean by decision error. Probability of making a correct decision if you rejected the true null, in other words, true positive, is how much?
0.9823.
23. In other words, 98.23%. If someone comes up to you and says, well, you rejected the null using an average of 105, that is the alternative, your research conclusion, standard deviation of 4. The chances that you made the correct call is 98.23%. Then, did you make a mistake?
Probably not.
Probably not. So you have a good amount of power. The chances that you made a correct decision based on the data you have is 98.23%. So you can be pretty confident that you made the right decision in rejecting the null.
Is there like a cutoff for that?
No, good question. Very good question. Is there a cutoff for power? There is not. All we want is maximum power of 1. Now, do keep in mind, I'm doing this under several assumptions, just to illustrate the concept of power, type 1 error, and beta, type 2 error, probabilities. In real life, this part, the power part, probability of beta part, completely hidden because it's theoretical. The only thing that you will see is alpha and beta. Good. So we are going over this just to illustrate the meaning of power, alpha, and beta. In real life, this part is completely hidden. This is for people, there's like me. Good. So I'm going to use the exact problem, the same problem here. And related to type 2 error next line, probability of type 2 error. And then it's going to move on to the next chapter before we run away. If you have to change something in this statement that I've read, like with this problem, where I use 105, what will you change?
You change the mean.
I will change the mean of 91 because my study no longer has a mean of 91, it has a mean of 105. That place to stop. Have a nice day. See you next time.